Okay. The last section that I'm going to cover in Chapter 6 is more applications of exponential functions. We're going to look at things called exponential growth and decay, Newton's law of cooling, and logistic models. This looks more intimidating than it really is. But here's the breakdown. So if you're a STEM major, a lot of exponential functions occur in fields like biology, chemistry, physics, etc., engineering. And the idea of exponential growth and decay, that shows up in a lot in biology and chemistry when you're dealing with populations of organisms that can grow, like, for example, populations of organisms that can grow without limitations, like bacteria, population of organisms that could grow without limitations. Examples include bacteria, insects, rodent populations could get really big. There's a lot of different organisms that could grow very, very quickly without limitation. That would be an example of exponential growth, which could be modeled by this equation. Now, what these variables in here represent, a sub 0, that's a subscript of 0, that's the initial amount of population. That's the initial amount of the population. That's the initial amount of stuff. That's the initial amount. The initial amount of bacteria, the initial amount of insects, whatever. T is the time period. That could be in days, weeks, months, years. It just depends on the problem. In this value K in here, that's called the growth constant. Now, since this is exponential growth, the growth constant is positive. So the growth constant is positive there. Now, in some applications, the same model, this is the exact same model as above, but sometimes there's not only exponential growth, but sometimes there's exponential decay. So things in chemistry and physics, the amount of stuff of some substance can decay over time. Like radioactive decay. That's a very common thing, like in, when you're dealing with nuclear energy, like in nuclear engineering. Radioactive decay, that shows up a lot in the real world. It's the same model. The only difference is, A sub 0 is the initial amount. So that's the initial amount of radioactive goo or whatever you got. Radioactive isotopes, whatever. The only difference is that since it's exponential decay, K isn't negative, or K isn't positive, K is negative. So really the value of K determines if it's exponential growth or exponential decay. Other than that, the models are exactly the same. All right? When we're dealing with exponential decay, there are some terminology things that show up that mean certain things. So sometimes in chemistry or in physics, something is referred to as the half-life of a substance. So what is the half-life? That's the time it takes for half of a substance to decay. All right? So the way we represent that, so if that represents the amount of stuff as a function of time, right? So this is the amount of stuff as a function of time. That would be 1/2 of the initial amount. That's how we would represent the half-life. That's how much time it takes for half of the stuff to be decayed. A lot of different, chemistry things, like, there's carbon dating, with skeletons, like with fossils. We could determine the age of fossils by looking at radioactive dating or carbon dating in the fossils of the bones of these, like, dinosaurs or anything. We could use half-life to determine the age of these things. Radioactive substance such as radium, which is a very unstable plutonium element. Radium is very unstable. If you're familiar with the Chernobyl nuclear accident, which occurred in 1986, the radiation that gave off from that place won't diminish for another 30,000 years. Like the half-life of some of the substances in that radiation have a half-life of 30,000 years, which means it'll take 30,000 years for half of that radiation to go to decay away. So, these things show up a lot in science fields. These phrases. So let's look at an example of such a model. So a colony of bacteria that grows according to the law of uninhibited growth is modeled by this function. A sub t equals 90 times e to the 0.0 t. So the amount of the population of bacteria is measured in grams, and t is measured in days. What is the population after 7 days? That's easy. Just evaluate the function at 7, because it's a function of time. So A evaluated at 7 is equal to 90 times e to the 0.06 times 7. So 90 times e to the 0.06 times 7 is 0.42. So when you type that in your calculator, right, so I'm going to have e to the 0.42 power times 90 is going to give me roughly 136.98 grams. So what is the population of this bacteria after 7 days? Well, if the initial amount was 90, after 7 days it grew to 137 grams. $136.98 grams. That's it. Just evaluate the function if you want to find the population after 7 days. All right. That's the unknown, so I want to figure out the function. All right. Now in number 2, it's saying how long will it take for the population to reach 250 grams? So what I'm saying here is how long will it take? I want to find t. Right? When the population reaches 250 grams. Alright, so that if my model is 90 times e to the 0.06 t, right? I want to find t when the population, so that's A of t, is equal to 250. All right, because A of t represents the amount of the bacteria after, t days. So you're just going to set this equal to 250 and solve for t. So 250 equals 90 times e to the 0.0 t. Divide both sides by 90. Before you take the natural log, get rid of the coefficient out front. Get rid of the 90 first. So 250 over 90, that reduces to what? 2.78. I'll just keep it as 250 over 90. Or, better yet, I'll reduce that to 25 over 9. Equals e to the 0.06 t. Alright, now that I have e to stuff by itself, I'm going to take the natural log of both sides. So I'm going to have natural log of 25 over 9, natural log of e to the 0.06 t. Now I could bring this out front as a factor. So the left-hand side is still ln of 25 over 9 equals 0.06 times t times ln of e. Well, ln of e are, they're inverses of each other, so they cancel out, which is really nice. So I'm left with 0.06 times t equaling ln of 25 over 9. And to solve this for t, you just divide both sides by 0.06. So we'll get t equals ln of 25 ninths over 0.06, which is approximately what? So natural log of 25 divided by 9 divided by 0.06 gives me roughly 17.03. So, to answer the question, how long will it take for the population of bacteria to reach 250 grams? It'll take roughly 17 days. That's it. Just like any problem, determine what your unknown is, right? Look at the problem, look what the question being asked. Here it's saying, what is the population after 7 days? So this is giving you the value of t. T equals 7. So just plug it into the function, see what you get. Here it's asking, how long will it take? So what is the t value when the population is equal to something? The problem's telling you what to find. Just once you know what it is you're finding, then you know what to do. From that point, it's just algebra. Okay. So in this example, I say the half-life of radium is 1,690 years. If 10 grams is present now, how much will be present in 50 years? So this is saying I need to build a model. I need to build an exponential model. So I need to build this kind of model. Since I know it's exponential growth, it follows this model. A is a function of time equals a sub 0 times e to the kt power. Alright, so when I'm building a model, I need to find k. I need to find the growth constant or the decay constant. So since this is radium, or this is dealing with like radioactive decay, k is probably going to be a negative value, but I need to find k. So to find k, I got to substitute the given information in. I need to find a of t. I need to find the initial amount, and I need the time. All right. Now, what's this saying right here? Half-life, right? There's that term again, half-life. Half-life means that's the time it takes for half of the initial amount to decay away. So if I have a half-life, right, that means the initial amount, or that means the amount at some function of time that means, because I have a half-life, that means A of t equals 1/2 of the initial amount. That's what it means when I say I have a half-life. All right. So I know what this part is going to be. That's going to be 1/2 of A sub 0. Well, what is A sub 0? What is the initial amount? 10 grams is present now. That's the initial amount. So that's what A sub 0 is. How much will be present in 50 years? That's the time. All right. So I know this. I know T. I know A sub 0. Now I can plug it in and find K. So when I do that, so remember, A of t equals, because I have a half-life here, this is going to become 1/2 A sub 0. And that's going to equal A sub 0 times e to the k times t power. Now t is 50. So that's going to be k times 50, or 50k. But the initial amount was 10. So I'm going to have 1/2 times 10 equals 10 times e to the 50k power. So now from here I could solve for k. So 1/2 of 10 is 5 equals 10 times e to the 50k power. We come up here, divide both sides by 10. So 5 over 10 is 1/2 equals e to the 50k power. Now I could take the natural log of both sides. All right, I could bring the 50k out front. ln of 1/2 equals 50k times ln of e. ln of e cancel. Divide both sides by 50. So that means k is going to equal ln of 1/2 over 50, which is approximately, so ln of 0.5, well, I'll use the fraction, divided by 50 is roughly negative 0.0, I'll round it out to 4 decimal places, so negative 0.0139. That's not the answer, that's just that's the decay constant. It's a decay constant because it's negative, right? So now I know my model is A of t equals the initial amount, which was 10, times e to the kt. So k is negative -0.0139 times T. That's my model. I could use this to find how much radium is left after T years. And that's the answer to the question. How much will be present in 50 years? So how much will be present in 50 years? So you're just going to put 50 into your function. So 10 times e to the negative 0.0139 times 50. That's a 50, by the way. Is what? You know what? I screwed this up. I completely screwed this up. I used the wrong value here. I shouldn't have used t equals 50. I should have used 1,690. Oh dear. That's what happens when you do these videos at 1 a.m. This is supposed to be 1,690. I'm trying to find out how much there is after 50 years. So I'm going to plug 50 in here, but to get the growth constant, I got to use 1,690. I'm so sorry, guys. So my logic was correct, I just used the wrong value. You're probably mad at me. I don't blame you. So yeah, the half-life is how much time it takes for half of it to go. How much time does it take for half of it to be gone? 1,690 years. So I put 50 there. I should have put 1690. It was a simple boo-boo. I'm sorry about that. So my growth constant isn't going to be, or my decay constant isn't going to be negative 0.0139. It's going to be natural log of 1/2 divided by 1690. So that's a very small number. That's a very small number. That's so K is going to be negative 4.10 0 times 10 to the negative fourth power. That's what that means. That's a very small number. So that's like you move the decimal point to the left 4 times. So 1, 2, so that's like 0.0004, negative 0.000410. So that's what the K value is. I'm sorry. So negative 4.10 times 10 to the negative fourth. That number times 50. That's in your that's your K value. All right. So this number times 50, e to that power, second answer, gives you that. Multiply that by 10. So that's how much will be remaining after 1,690 years, roughly 9.79, well, 9.80 grams. So everything here is correct except this value. I picked the wrong value. I knew I should have picked 16. Well, I just didn't realize I picked the wrong value until I got there, because when I did the computation, it didn't make sense. I would get, if I had did this with the incorrect decay factor, it would have given me 5, which doesn't make sense. So yeah, I'm sorry, but hopefully that made a little bit more sense. Hopefully you're okay with that, but if you're not okay with that, don't worry about it. If you could follow along with it, great. Just, yeah. The only reason I use 1690 here is because that's what the half-life is. The half-life means it takes 1,690 years for half of it to decay away. Okay? If you're watching this and you're in my fall 2020 section, don't worry about this problem. Let's look at Newton's law of cooling. So what this does is it measures the this measures the temperature of a heated object and how long it takes to cool in an environment. It follows exponential modeling. So the temperature, which we denote with, well, your textbook does with a fancy U, of a heated object at a given time is given by this equation. So T is the constant temperature of the environment. U sub 0 is the initial temperature of the heated object. Of object at T equals 0. Right? When I start, once the object is introduced to the environment, its whatever its temperature is U sub 0. And K is a negative constant. And it's negative because the object is heated, and once it's placed in an environment, it starts to cool. The temperature begins to decay. That makes sense. Every time I pour a cup of coffee in the morning, as it sits there when I'm teaching, it's as hot as it was going to get as soon as I poured it in my cup. But as I start teaching and as I sip it, it gets cooler and cooler. It obeys Newton's law of cooling. My cup of coffee. All right. Let's look at a problem that deals with that. And An object is heated to 100 degrees Celsius. It's then allowed to cool in a room whose air temperature is 30 degrees Celsius. If the temperature of the object is 80 degrees Celsius after 5 minutes, when will its temperature be 50 degrees Celsius? Oh boy, a lot of information here. So we know we're dealing with Newton's law of cooling, so it follows this model. T plus the quantity, u sub 0 minus T times e to the kt power. Alright, so if I want to find my model, I need to find K again. I need to find the negative constant. Hopefully I don't make any mistakes here. So the object is heated to 100 degrees, so I need to find my information, right? The temperature of the environment, the initial temperature of the object, yeah. So what's the temperature of the environment? So it's in a room whose air temperature is 80 to 30 degrees Celsius. So the temperature of the environment, and it's constant, so T is 30, right? The initial temperature of the object, once it's introduced to the environment. So an object is heated to 100 degrees Celsius, right? So once it's heated to 100 degrees Celsius, then it's placed in the room. So as soon as it's placed in the room, it's initially 100 degrees. So that's the initial temperature, 100 degrees. Alright. Now, if the temperature of the object is 80 degrees Celsius after 5 minutes, so that means, so this right here is the temperature of the object after a set amount of time. All right, so that means after 5 minutes, the temperature is what? 80 degrees. All right, this is the temperature after 5 minutes equals 80 degrees. So this is my given information. I want to use this to find K. So my model will be 80 equals 30 plus the quantity 100 minus 30 to the times e to the k. Now t here is 5. So k times 5 power, 5 minutes. So I'm going to have 80 equals 30 plus the quantity, 100 minus 30 is 70, times e to the 5k power. I could subtract 30. I'll have 50 equals 70 times e to the 5k power, divided by 70. 70s cancel, so I get what? I get e to the 5k power equals 5/7. Right, 50 over 70 reduces to 5/7. Now from here it's the same process. Take the natural log of both sides. You could bring the 5k out front. The ln of e cancel out, so you're left with 5k equals ln of 5/7. Divide both sides by 5. K equals ln of 5/7 all over 5. Natural log of 5 divided by 7 divided by 5 is negative roughly 0.0673. If I go to the 4th decimal place, So my model is no, let me write it down here. So my model is U is a function of time so the temperature of the environment is what? The temperature of the environment is T, right? So it's 30 plus, now we know the initial temperature is 100. We know the temperature of the environment is 30, so 100 minus 30 is 70. So plus 70 times e to the negative 0.0673 times T power. That's my model. That measures the temperature of the object after T minutes. So to answer the question, when will its temperature be 50 degrees Celsius? So when will its temperature be 50 degrees Celsius? So that means I want to find T when the temperature is equal to 50. So that means when this is equal to 50. So I'm going to have 50 equals 30 plus 70 times e to the negative 0.0673 T. Subtract 30 from both sides. Boom, boom. I get 20 equals 70 times e to the negative 0.0673 T. Divide by 70. 20 over 70 is 2/7. E to the negative 0.0673 T. Take the natural log of both sides. You know the drill by now. Take this whole thing, bring it out front. Ln and E cancel, so you're left with Ln of 2 over 7 equals negative 0.0673 T. Divide both sides by negative 0.0673. So T equals this thing. Now 2/7 over negative 0.0673. Type that in your calculator. Divide it by negative 0.0673. Gives me 18.61. So in order for the object to cool to 50 degrees Celsius when it was initially, or after 5 minutes, you know, the object was heated to 100 degrees, it was put in a room that was 30 degrees. So it'll become 50 degrees after 18 minutes, and so roughly 18, 19 minutes, it will be 50 degrees Celsius after roughly 18 to 19 minutes because of that value right there. So that's a long problem. But you guys are doing big boy algebra now. Okay. The last thing we're going to look at is something that we call a logistic model. So what is a logistic model? A logistic model, exponential models look like this. You know this already from the behavior exponential models. They do something like that, right? They grow exponentially. That's exponential. A logistic model, however, this is not logarithmic, this is logistic. Don't confuse the two. So logistic models, they have exponential behavior. They start off exponentially, but they don't remain exponential forever. Let me get rid of the subheading here. It's killing my vibe. Exponential, that takes off and it goes up forever. Logistics models don't do that. They go up, but eventually they start to flatten out again, like this. That's a logistic model. And it approaches a horizontal asymptote. Y equals some horizontal asymptote. Alright? So that's what a logistic model looks like. You know, they don't grow exponentially forever. It hits this horizontal asymptote. And the reason why it doesn't that is because this population has limiting factors like food supply, living space, and it can't grow forever. It can't sustain itself. The human population is a logistic model. You know, at some point, Earth is going to be overpopulated. It is now already, but if the population continues to grow like it does, eventually it won't go any higher because it won't be able to support itself. There won't be enough food, there won't be enough space for everybody on Earth. The human race is a logistic model. A lot of other populations are logistic models. And this is what a logistic model looks like. So the logistic model is increasing if B is positive, and it's decreasing if B is negative. That's the growth rate, this value of B right here. That negative in front of it is not part of the growth rate. That's just part of the model itself. Okay? As time goes on, the logistic model approaches this horizontal asymptote up here. Well, the horizontal asymptote can actually be represented by the value C right here. And that's called, it has a specific name. That horizontal asymptote is the carrying capacity of the model. That represents the value of the model would approach as time goes on forever. So, you know, as time goes on forever, the population is going to approach some limiting amount. It's going to approach a carrying capacity, which means it won't go any higher than that. The population can't exceed that value, otherwise it won't survive. Because there's not enough food, there's not enough water, whatever. So the logistic model is increasing if B is positive, and it's decreasing if B is negative. There are two horizontal asymptotes, y equals 0 and y equals c. So technically I should have put a c here, but and y equals 0 is the one right here. That's what a logistic model looks like. I guess I could do better here, huh? Goes up exponentially, but then it starts leveling out again. That right there is the horizontal asymptote, y equals c. And this right here is the horizontal asymptote. Well, actually, this is the horizontal asymptote, y equals 0. So that's kind of what a logistic model. It looks like a flattened S. So yeah, that's the association of the carrying capacity is this value. It's the horizontal asymptote up here, and this is increasing. A decreasing one would be going down, like it would be a backwards S. So here's an example of a logistic model. And that This logistic model represents the population in grams of a bacterium after T hours. Now, I know I said bacteria represents exponential growth, but some populations of bacteria don't grow exponentially, they grow logistically. Sometimes they do have carrying capacities. So what is the growth rate? Well, the growth rate is this value right here. All right. The growth rate is the value that you see right in front of it's the value in front of the t variable. So the growth rate is B, which is negative 0.439. So this logistic model has a growth rate of what? If I move that to the right, if you write this decimal point as a percentage, it's 43.9%. Because the growth rate, we're just looking at the value. We're looking at the absolute value of this. Because in your notes, right, the value of absolute value of B is the growth rate. So if you have negative B there, just take the absolute value of that. That's the growth rate, which is 43.9%. Okay? Determine the initial population size. The initial population size. So how do you do that? Well, if you're looking at initial population, you're looking at what the value of this is when t is 0. So you're just plugging 0 into your model. So when you do that, what are you going to get? I just needed to check something in the textbook. It's not a problem. So you just replace t with 0. So you're going to have 1,000 over 1 plus 32.33 times e. So now if I look at the power, I have negative 0.439 times t. Well, I know t is 0, right? That's what this means. I put t equals 0, I popped it in my function. So I have that number times 0, so that's going to be e to the 0 power, right? But I know that e to the 0 power is 1, right? You can check your calculator. Anything to the 0 power is 1, except for 0, of course. That's 1. That was a property, actually. So I have 1,000 over 1 plus 32.33 times 1, which is this 32.33. So that's going to be 1,000 over 33.33, which is 30.33 30.003. All right, there's the calculator right there. So 30.0. So the initial population of bacteria was 30 grams. What is the population after 9 hours? All right. That's just another question. You know, I'm trying to find the population. So you just pop 9 into your model because T is 9. So you're going to get 1,000 over 1 plus 32.33 times e to the, so what, negative 0.439 times 9. So go through that in your calculator. So let me do the E part first. So negative 0.439 times 9. So I'm going to raise e to that power. So second e, second answer gives me that. And that's being multiplied by 32.33. And then you're going to add 1 to that. So you're going to have 1,000 over 1.621882315. And when you do that, so 1,000 divided by second answer gives you 616.57. So how many, what's the population after 9 hours? So after 9 hours, it's approximately 617 grams. You know, initially it starts off pretty small, and that makes sense, right? Because a logistic model, just like an exponential model, starts off pretty small, grows really quickly, but then it levels off. When will the population be 700 grams? So you're trying to find T. When P of T equals 700. So you're going to set this model equal to 700 and solve for T. Okay. Well, so what I'm going to do here is I'm going to cross multiply. I'm going to cross multiply there. And when I do that, I get the following. So I'm going to get 1,000 equals 700 times the quantity. 1 plus 32.33 times e to the negative 0.39 t. Divide both sides by 700. Boom, boom. 1,000 over 700 is that, but as a fraction, 10 over 7 equals what? 1 plus 32.33 times e to the negative 0.439 t. Subtract 1. That gets rid of the 1. Let me come up over here. So 10 sevenths minus 1 is what? 10 sevenths minus 7 sevenths is 3 sevenths, right? Equals 32.33 times e to the negative 0.439 t. Divide both sides by 32.33. They cancel out. So you're going to have e to the negative 0.439 t equals this junk, which is on your calculator. So, right, 10 divided by 7 minus 1 was 3 sevenths, right? 3 sevenths divided by, divided by 32.33 gives me that. So 0.013256, that's good enough. Take the natural log of both sides. L and E cancel out. You bring this down front. L and E cancel out. So you get, what, negative 0.439 t equals natural log of this, right? Divide both sides by negative 4.39. So you're left with t equals the natural log of 0.013256 over negative 0.439. And that'll give us a grand total of what? So natural log of this answer, right? Second answer gives us that, divided by negative 0.439, 9.85. So when will the population be 700 grams? Roughly 10 days. Or wait, no, is this in hours or days? It's in hours. So roughly 9.85 hours. Da-da-da-da. This material can get a little tough. But, you know, you're doing big boy stuff now. So, I apologize about this part. You know, I really screwed up on that one just by picking the wrong value. I meant to pick 1690, but for some reason I just wrote 50 there because I'm running on fumes, but, you know. So that's all the material I'm covering. Don't worry so much about, you know, everything you need to know. Just focus on what we, you know. Yeah, so that's the end of the video.